Welcome everybody. Thank you for coming. I am Aditya, as he told, and I'll be in the next 1 hour talking about receivers and receiver nonlinearity. Most of the time in wireless communication systems, we are fixated with transmitters. What is the transmit power? What is the transmit mask? And how much interference a transmitter causes, etc. But especially in dynamic spectrum access scenarios, receivers play a very important role. And why it is, I'll be discussing in the next 40 minutes. Uh, what I want you to take away from this talk, hopefully, I'll be able to convince you that receivers are as important, or rather more important in dynamic spectrum access networks than transmitters themselves. And why is that? How? I'll be just telling you. So I'll initially introduce you to the challenges in dynamic spectrum access, which are not specific to my talk, but the general challenges, and how we reduce those challenges to my specific problem. And what is receiver nonlinearity and why it plays an important role in dynamic spectrum access? What are the key questions addressed in this talk? And background on adjacent channel interference and the ongoing efforts. So that forms a big background. And then I'll talk about a couple of problems that I have worked on just to give you an idea of how receivers can actually play out an important role in dynamic spectrum access networks. This is a world famous graph in wireless communications community. Uh, Exponential increase in wireless demand. It's really bad out there. The congestion, the spectral congestion. We need to do better than what we've been doing. So dynamic spectrum access is a very promising technology to address the increasing spectral congestion, because a lot of spectrum is not used at most of the times. So utilization of the otherwise unused spectrum is important to maximize our spectral efficiency and spectral utilization. So in order to advance dynamic spectrum access, FCC very recently initiated the topic of SAS, or the spectrum access system, and told that SAS can actually manage spectrum in real time. Now, SAS will manage any shared spectrum, with specifically starting off with the 3.5 gigahertz, it is going to manage a lot of shared spectrum. But the challenge of the SAS is that it has to manage diverse radio access technologies, diverse aspirations. As shown in this figure, it will be managing maybe an emergency transmitter, a radio astronomy transmitter, which requires very good sensitivity, so it requires a lot of interference protection, and of course the cellular and Wi-Fi technologies. So these are all different radio access technologies. I'm not talking about the modulation or the physical layer of it. The devices themselves, the receivers themselves are different. The RF is different. So we need to be able to account for the differences and their aspirations, and they're different for a reason. GPS cannot be same as our LTE receivers. So in a shared spectrum scenario, we have to account for the differences and then design in real time the spectrum allocations. Moving forward, the challenges are, as I already told, heterogeneous technologies. By heterogeneous, I mean heterogeneous in the RF front-end part. The diverse devices and their aspirations in terms of quality of service. And in doing all these things, we have to maximize the spectral efficiency and then protect all the users, all the interested parties from interference. Now, this protection of interference is different from from protecting primary users from interference. Imagine a shared spectrum space where primary is absent and tens or hundreds of secondary users are accessing that spectrum. Each of those users also have to be protected from interference from each other. So that is the scenario I will explore. Of course, primary protection is anyway there, and that has been looked into with some detail. Now, why is receiver important? This is a very simple model of a receiver. It does not represent all the architectures, but we have a pre-selector filter here, which decides how much of the spectrum is input into the RF front end, how much spectrum gets inside my RF chain. And then we have the front end, which includes LNA, several stages of frequency down conversion and mixers, and then ADC, etc. Now, I treat that as a black box for the purpose of this talk, and then argue that that can be modeled as a nonlinear system. So the complete box there, the dotted line box, will be taken as a nonlinear system, and then we have a filter sitting in front, which decides the amount of spectrum input to the receiver. So with that background, I'll just briefly tell you what are the key questions addressed in my talk. Firstly, I want to state a fact that receiver nonlinearity, that box what I told, it adversely affects interference. Now, how does it impact, it adversely affects performance, I'm sorry. How does it affect the performance? And is it possible to quantify the performance degradation? The answer is yes, and I'll be talking about that. The second question is the fact that receivers need protection from adjacent channel interference. So because of the nonlinearity, the receivers are, the frequency response of receivers are not linear. So adjacent channel signals can affect in-band signals. So that is the adjacent channel interference, and I'll talk more about it very soon. So if we have to protect receivers from adjacent channel interference, how can we do that? So how can dynamic channel allocations be customized for receiver performance tolerance limits? So why do we stress a lot on receivers? I would like to briefly introduce on transmit and receive masks. This is something that we all are familiar with, the transmit mask, in which we have a signal and then there is a certain roll-off characteristics prescribed by either the standard or a regulatory body that, for example, LTE or any other signal, in-band to out-of-band ratio is prescribed. And traditionally, receivers were designed to match with these transmitter characteristics. But in the dynamic spectrum access scenario, what the receiver tolerance limit is also important. So the DISPAN 1900.5.2 standard came up with something called as a receiver mask, which is a complement of the transmitter mask, which says how much interference can a receiver take in. So in band, the interference that the receiver can take in is very low, which amounts to co-channel interference. But in the adjacent channels, receivers can take in some amount of interference depending on how far the adjacent channel signals are. So this is the receiver mask. Now this receiver mask typically gets dictated by the preselector filter that I talked about. So if the preselector filter is very wide, then the receiver masks are also very wide, and vice versa. So a combination of these two actually decides how much of signal comes into my preselector, what happens, and what are the input signals. Now, why is this important all of a sudden in dynamic spectrum access or in heterogeneous systems? Traditionally, let us take, for example, a GSM cellular system. We had a transmitter with that transmitter mask, and the GSM standard prescribed a particular receiver performance standard. The standard describes how much of a tolerance limit a receiver should have. Based on that, the preselector filter was designed. And then, even if we had adjacent channel signals, it wouldn't matter because everything was pre-planned in that, for that GPS, for that GSM band, everything was pre-planned. And if it was between bands, then what the FCC did was, okay, this receiver needs to have a very wide preselector filter or a very wide receive mask, so we shall allot a carefully planned guard band between the two bands or between two transmitters. And the guard band also accounted for the transmit mask. But in dynamic spectrum access scenario, say we have a receiver with an arbitrarily large receive mask, but the transmitter has a different kind of transmit mask or the different kind of transmit specification. And the same spectrum is also used by various other technologies which do not necessarily have this requirement prescribed for this particular receiver. In other words, there may be many other transmit signals received by the receiver due to the preselector filter. So this becomes a problem when different radio access technologies access the same spectrum. Otherwise, it wouldn't have been a problem as in the GSM or in the other pre-planned scenarios or static allocation scenarios. This becomes a problem in dynamic spectrum access scenarios. Then there may be another receiver with a totally different receive mask, and that may have a different transmitter. So as you can see here, the two receivers are receiving different number of signals in their preselector filter. Their interference hence is different, and their protection requirements are also different. So we need to plan for all these things in a dynamic spectrum access scenario and work out strategies to avoid interference. Why do we care about receiver nonlinearity? This is a very popular model, also a very classic model for receiver nonlinearity. It is not the only model, but the most popularly observed model in the literature and as well as in the industry, also in the data sheets. So ideally, we would like to have only the linear term in that expression, but we don't have the only, we have the nonlinear terms as well, which contribute to the interference. How exactly do they contribute? Now let us consider in particular to the third order term here. Let us say that in a preselector filter, we have a desired signal omega naught, and then we have two adjacent channel interferers, omega 1 and omega 2, and they are equally spaced. So if we take that signal and then cube it, as happens in the V cube term, if you consider simple sinusoidal signals, what happens is the omega 1 and omega 2 produce an intermodulation term, or they interact with each other and produce an interfering term at the desired signal, which is omega naught. This is called as an intermodulation. And this is a scenario if only two adjacent channel signals are present. Imagine if there are a lot of adjacent channel signals, a lot of different varying powers, varying bandwidths, what would happen? So in order to measure the nonlinearity, so alpha 3 there gives you an extent of the nonlinearity of the V cube term. Now, it is not very straightforward to measure alpha 3, so there is a technique wherein we extrapolate the first order and the second order responses until they meet on the power scale, and then that is called as the intermodulation intercept point. You don't have to worry a lot about that. That just tells you how good or bad a receiver is, so the extent of nonlinearity. So if IIP3 is infinity, that means alpha 3 is 0, that means the receiver is very good. If IIP3 is not infinity, that means the receiver is nonlinear, which is the practical case. So how exactly does an adjacent channel interference affect me if I have a lot of signals? In the upper panel figure there, I have a lot of adjacent channel signals, and this particular thing is my desired channel as labeled there. So that is my desired channel, and then I have a lot of adjacent channel signals. Just pass it through a cubing function. This is a simulation, and then you can see the third order noise, which flares up in the red. So that is the adjacent channel interference. So my noise floor, which was way below, now has suddenly gone up because of the intermods, and then it causes interference. And another interesting aspect to note is that that noise is not even white noise. It is a frequency selective noise, or it's a colored noise. And how can such a nonlinearity affect me? That is given in the figure below. In a traditional system, let us say we have only a co-channel interference, and we have the interfering power fixed, and then we vary the desired channel power. So as we vary the channel power, my received signal to interference ratio increases linearly because the interference is constant. But because of the nonlinearity, what happens is beyond a point, increasing even my own power hurts me because of saturation, because of various other phenomena that happens due to nonlinearity. So nonlinearity can actually be a killer in terms of the performance, especially in dynamic spectrum access scenarios where adjacent channel signals are not of our own kind. So knowing that nonlinearity affects, how can we plan for it? This is a classic diagram. Okay, I should not call it classic, but this is a diagram from the PCAST report, which said that in the upper panel, say I don't know anything about the receiver. I don't account for receiver performance or the filter characteristics, and then I do a blind frequency allocation. All I can do is allot channels randomly. So there is a very high probability that an adjacent channel signal falls into my own preselector and causes interference. The lower panel illustrates that if I knew the receiver characteristics, I could technically rearrange it, repack it in such a way that they don't interfere. So knowing receiver characteristics can actually be a boon. Another example of why consider receiver performance is the light squared controversy, which blew up about 3 years ago and created a lot of economic and wireless problems. So GPS receivers are known to have very poor selectivity because they have to be very sensitive. Light Squared is a company which wanted to deploy LTE repeaters in a band adjacent to the GPS repeaters and obtained FCC license, and then they also were ready for deployment. But after that, at this stage, the GPS community raised an alarm telling that even though they are in the adjacent band, they cause interference to the GPS receivers because our selectivity is poor. And due to this reason, FCC suddenly got alerted and they did more testing, and eventually they had to revoke the license of Light Squared, because of which Light Squared suffered a huge loss. They filed for bankruptcy, and also all the wireless benefits that came along with those LTE repeaters were not available, or it was basically taken away. So such kind of mishap may be a strong word, but such kind of controversies can be avoided if prior to allocation, now we are talking about static allocation. Now prior to allocation, had the receiver characteristics been taken into account, then Light Squared would not have gone through all this ordeal. Imagine in a dynamic scenario, what would happen? We basically would not get any throughput at all. So this is one example. Another example of receiver diversity is what we did a small experiment in the lab here in Durham. In the 3.5 gigahertz, taking that as an example, there is a spin 43 radar signal that is present, and then we took two receivers, commercially available, LTE and Wi-Fi, and then swept across in bands co-channel and in adjacent channel to the desired signal. So what I mean is, LTE bandwidth was 10 megahertz because that was the equipment. So from here, 10 megahertz, which is I've taken from the center frequency. So I have an LTE bandwidth of 10 megahertz. I take a radar signal and sweep it, and then I have a Wi-Fi bandwidth of 20 megahertz, and I take the same radar signal and sweep it and measure the performance. When I'm sweeping it co-channel, I would expect a lot of performance detriment. So as you can see, the throughput is very low. In this region, the throughput for both Wi-Fi and LTE is very low. But as soon as I move out of the co-channel region, LTE achieves 100% of its throughput. So LTE's adjacent channel rejection is very good. But Wi-Fi, turns out, even if I go a gigahertz away, it does not seem to achieve 100% of its throughput. Now, initially I thought this must be wrong. I mean, I must be doing something wrong. But when I read up the specs of the Wi-Fi receivers, it turns out that Wi-Fi operates in two bands, 2.4 gigahertz and 5 gigahertz, and they have a single preselector filter covering both. So they have a wide preselector filter, and any signal that falls in which is of a sufficiently higher power will interfere with my desired band. Will interfere with my Wi-Fi signal. So that is why it takes so long to achieve 100% of its throughput. So in doing all these things, what are the ongoing efforts? The model-based spectrum management of the IEEE 19.5.2 standard have told that we will prescribe certain receive masks, or rather the communicating the receive masks should be compulsory for SAS, but they have not necessarily told how to arrive at them. The FCC Technological Advisory Committee also released a report telling that receiver should have something called as a harm claims threshold, which means that in an adjacent channel, if a particular signal is over and above a pre-prescribed threshold, only then receivers can claim interference. So it treats interference as binary, either existent or not. It's good for an initial analysis, but we can do much better than treating interference as binary. The ITU report, long time, so many years ago, I think almost 20 years ago, ITU had released a report telling that two signals can cause intermods, and then how to deal with it and how to calculate interference. And considering only two signals was enough 20 years ago, it's not enough anymore. And more recently, Preston Marshall did an approximate analysis of two-tone intermods. I tell approximate analysis because if there are n signals present in my preselector filter, not all n of them interfere with me depending on my desired position, the position of the desired signal. But he considered that everything interferes with me and did an approximate analysis just to arrive at some result. So the problems addressed in this talk are two. What is the impact of front-end nonlinearity on performance? And how can we characterize the receiver nonlinearity by quantifying how much detriment I get? Secondly, can I use that knowledge to do real-time allocations in a dynamic spectrum access scenario? Let's go to the first problem. We want to represent how adjacent channel signals affect the desired signal. So let us take a preselector filter and channelize it into n channels. And we have the power received in each of the channel reduced to the amplitude. A represents the amplitude because the cube term in the polynomial approximation it represents the amplitude, not the power. So we have to deal with the power. Now I want to clarify that by amplitude I don't mean we have to demodulate it or we have to recover the symbols. It is just that we have to bring down the power level to the amplitude level. So we have amplitude version of power spectral density. It's not exactly a power spectral density because it is not 1 Hertz, but something similar to that. Now, adjacent channel interference in the time domain is a cubic term. So the third order nonlinearity in the time domain is a cubic term. And in the frequency domain, it will be a double convolution, which can be represented using Toeplitz matrices. Toeplitz matrices for convolution has been used before, and we can form a Toeplitz matrix using the received amplitude vector and then describe the adjacent channel interference as shown in that equation there, which is rho. This is the adjacent channel interference where Q and R are Toeplitz matrices as shown. Now, is this good enough? What happens is, say I'm trying to calculate the SAS is trying to calculate adjacent channel interference or trying to make some real-time allocations, and then one of the signals goes away or something changes. One of the transmitters has to change the channel. Now, what happens in that Q matrix? Say A2 suddenly goes to channel 1. So I have to rewrite, if there is a single change in one of the amplitude values, I have to rewrite two matrices. So I have to change at least n values in one of the matrix, at least n values in another matrix. So it's a lot of, it doesn't offer me flexibility. In addition, this is not a very convenient form for utilization in real-time allocations. In that, if I want to pre-multiply this with a permutation matrix, which represents the channel allocation matrix, it doesn't give me a convenient form. I cannot just pre-multiply it with some matrix and then try to change the channel allocations. And hence, we want to improve this model. So let us look into what characteristics are of the interference or the intermods. Because we are dealing with third order intermodulations or third order nonlinearity, we have two kinds of intermods that affect us. One is a two-tone intermod. So any two adjacent channel signals combine to form interference or to produce interference at a desired channel. So the distance or the separation in frequency between interfering signals should be equal to the separation in frequency between one of the interfering signals and the desired signal itself. So the two red arrow, so basically A2 and A3 here cause interference, combine to cause interference. A3 and A5 combine to cause interference, but A4 itself does not cause any interference. This is for a specific case considering A1 is my desired signal. Now if we want to generalize it, we can use certain combinatorial analysis and then come up with what are the adjacent channel signals given a location and our preselector filter which is channelized, what are the adjacent channel signals that actually affect it. The next is three-tone. Since it is a third order intermodulation or a third order distortion, any three signals can combine or can interact with each other to form intermod at my given at a given desired channel, so long as they satisfy that particular condition where n is my desired channel and I, j, k are the indices of an adjacent channel signal. So long as they actually satisfy this relation, so this is an example of 1, 2, 3, 4, wherein 1 is my desired channel and 2, 3, 4 interact to produce interference. Again, using certain combinatorial techniques, we can come up with sets, triplets, which at a given position tell what are the total adjacent channel interfering signals. So using this, we can come up with a formulation which is more flexible. I'll not go into the details. I'll just use the formulation to show how exactly the adjacent channel power is formed. Let us consider a very simple uniformly distributed power spectrum in the adjacent channels. So the power spectrum is given by A of f, and then it can be shown that the adjacent channel signal is given by that particular expression there. So what this shows, that figure shows is with varying ratio of signal to preselector bandwidth. So what do I mean by that? The signal bandwidth is how much ever my signal occupies in the entire preselector, so which is W here. And the total preselector bandwidth is B. So as a function of W by B, I have plotted the adjacent channel interference. So as W by B increases, so beta equal to 0 means I'm not using any channel itself, I'm not using any spectrum at all. Beta equal to 1 means I'm using the entire preselector filter. So as I increase my beta, there is a variation in the adjacent channel power, which is shown in that particular figure. Now this should contribute somehow to my capacity detriment. How can I map this to performance, to quantify the performance of my receiver? We all know that the Shannon's limit is given as shown in the top equation there, and then the for a channel with varying power, we have the equation as shown there. We again consider a simple case of uniform power distribution, and then with adjacent channel interference, with varying adjacent channel interference, we have a varying noise, because we treat interference as noise for this purpose because it may be cross technology. It may not be very easy to cancel. So we have a frequency selective power, we have a frequency selective noise. So in this case, water filling algorithm gives the optimal solution of how to spread my power across frequencies, where the water filling level is given by that particular expression there. Now using this, I plotted the capacity for a uniform distribution case, and as you can see, with increasing nonlinearity, I take a capacity hit. So the blue curve, which is the topmost curve there, represents without any nonlinearity. So if the receivers were perfectly linear, what is the hit that I take? I mean, if the receivers were perfectly linear, the blue curve represents the capacity, and if the receivers are nonlinear, what is the hit that I take? Using some simple receiver performance metrics, we can get a feel of how much of a detriment that I am actually the receiver is suffering, or the performance detriment that I suffer due to nonlinearity. It turns out that for low, in 3.5 gigahertz, for example, we have 150 megahertz of bandwidth, and my signal bandwidth, or my own desired signal, may be 1 megahertz or maybe 10 megahertz. So that means in the beta, which is W by B, is 1 by 150 or 10 by 150, which is very low. So as you can see here, for very low values of beta, I suffer a lot of loss. The capacity loss that I suffer is immense due to the third order nonlinearity, and it increases, of course, with increasing nonlinearity. So the takeaway points: receiver nonlinearity can adversely impact the interference, and receiver performance should be accounted during spectral planning and dynamic spectrum access to improve the spectral efficiency. How can we do that? I'll spend the following minutes trying to explain that. So in the first case, I take just two receivers and then show how considering the nonlinear effects only in a two-user case can improve the spectral efficiency. And then I do channel allocations with n user and then show the performance improvement. So what is the system model? Say I have a normalized bandwidth of 1 and say I have two users using that normalized bandwidth, and then signal 1 and signal 2 are the received signal powers of those two respective receivers. There is an overlap which basically causes interference with the adjacent receivers. So the shaded portion of blue causes interference with the red signal, and the shaded portion of red causes interference with the blue signal. So how can we account for the interference caused, and how can we optimize over the power and the frequencies? So what is the very naive upper and lower bounds? We can at least do as good as this. So if we don't allow any signals to overlap, we give a guard band in between, and then we say transmitted using so much of a bandwidth. This wastes a lot of frequency. Is this the best we can do? We don't know. The best we can do, theoretically, if the receivers were perfectly linear, is I use the whole spectrum, entire available spectrum. So I cannot do this as well because the receivers are nonlinear. So in practice, the optimal point has to be somewhere in between. So we calculate the adjacent channel interference, which is a function of the receiver parameters and the received power itself, and then tweak the frequency. So the FH1 here, this point, and the FH2 here, this point. So what is the optimal point? How much can I push into the adjacent channel? And then that also depends on the power allocations. So if my power is high, it depends how much I can push. So we do some optimization over this. And then compared to the naive allocation is I give the perfect guard band between the signals. That is a green line below. So if I knew what the exact receiver parameters are, it turns out that I can do much better for very bad receivers. So the left side of this, minus 30 dBm of IIP3, means that the receiver is very bad, and 0 means the receiver is relatively good. So if I didn't know how good or bad my receivers are, I'm stuck with the green line because I have to allocate so much of power, so much of guard band, because I don't know how my receivers interfere or how much my receivers tolerate. But if I know the receiver characteristics, as my receivers get better and better, I can actually achieve the maximum, which is the best case scenario. So this is a very interesting example of a two-user case. Also, the developed framework here does another interesting thing. Say there are two receivers, one which is good and the other which is bad. So what happens in that case? So we fix the IIP3, which denotes the nonlinearity of one of the receivers at minus 20 there, and then vary the IIP3 of another user from minus 30 to 0. So long as the receiver, the user 1's IIP3 is worse than the user 2's IIP3, it receives a lower data rate. The blue line there, it receives a lower data rate. As soon as the receiver 1 gets better, it jumps up, and then this fellow jumps down. And it maintains a minimum rate constraint which is prescribed. So it penalizes bad receivers and gives benefits to good receivers. So there is an inherent market play also. I won't go into the details, but there is an interesting market play also which can result in a planned obsolescence of poor performing receivers. Now this was a two-user case. Now consider n channels and n users. So for simplicity, I fix the bandwidth and power in this particular case because it's a combinatorial problem. So what is the best arrangement? The system model here is I have a transmitter and I have n different receivers, and each receiver suffer adjacent channel interference. What is the best arrangement of receivers that I can make depending on the received power and the number of interfering signals that I will get the best data rate? These are certain system model parameters where n is the total number of channels and etc. I will go through that as I explain more. So what happens? Say I have n signals and one of the guard bands is PBM, or the preselector filter, not the guard band, I'm sorry, the preselector filter is PBM, that is the preselector bandwidth, and that spans 3 signals. And for another receiver, it may span only 2 signals wide. So the number of signals that I am getting interference from is given by that equation there. So it is a 0 or 1. Given a signal j, okay, and the receiver placed at a location n, I receive interference from j if that condition is satisfied. So this has to be written more in a more favorable manner for optimization using certain combinatorial analysis. Given a location I and for a channel n, so what are the number of interfering signals? So that particular expression gives me how many signals given a particular location in the whole spectrum, where if I place how many interference signals actually affect me depending on my preselector filter. So using this, I again do some sum rate maximization. So that is the sum rate over n users, which is the numerator gives the received power and the denominator gives the adjacent channel interference. This is a hopelessly nonlinear non-convex function. So it is very tough to optimize over that particular function. So we lower bound that function using pushing that summation inside using Jensen's inequality. This particular summation can be pushed inside using Jensen's inequality, and then we can lower bound it. Now look at this equation here. So if I want to maximize R, it is, there is no variable here in the first term that I have to play with. I have to play with only the variables in the second one. So I have to minimize this term here because there is a negative sign here. So maximizing R involves minimizing this second term, which in turn means minimizing the sum adjacent channel interference. That is something I can work with. So the new objective function now is summation of the adjacent channel interference, and then to deal with this I define a permutation matrix, which is a channel allocation matrix, which basically is only ones in any row or column. So that is the channel allocation matrix. So for solving that optimization problem, I come up with a greedy algorithm, which is as shown here. So we form something called as an adjacent channel interference matrix. So in any given channel, if I place a given receiver, what is the interference that it faces? So this particular term here, or this particular entry here, tells if this nth receiver is placed in the second channel, what is the adjacent channel interference it gets. Similarly with all other entries. So given a receiver, if I place in the first channel, what is the interference, and so on and so forth. So this gives me the adjacent channel interference. So my problem can now be written as the adjacent channel interference is the trace of m into k, where m is my allocation matrix. So my permutation matrix multiplied by this, and if I take the trace of that, that gives me the sum adjacent channel interference. And then I need to minimize that particular term. So to do that, I propose a simple algorithm. Say I have the K matrix. Now I want to minimize the multiplication of this K matrix with another permutation matrix. So what I do is I choose the minimum value possible and then allocate that particular receiver to that channel and then cross out that row and column. And then take the next minimum, which is remaining among the rest, and then cross out that row and channel, and then go on doing that until I allocate all receivers. This is a greedy algorithm. It is not optimal, but it is better than, because uh, binary integer assignment problem is NP hard by definition. So we need to come up with some algorithm to solve the channel allocation problem. And then doing this, we get a lot of improvement. So as we change the transmit power, we enter more into the nonlinear region. And as we go more into the nonlinear region, we can see that the gain due to the receiver cognizance or the receiver awareness is pretty high. I can discuss more about the details of the algorithm or the framework itself. I didn't want to go into the details of it. I just wanted to give you an idea of how receiver performance can actually impact the network efficiency and the network performance. So in this talk, I talked about tractable representations of nonlinear distortions. How can they be represented, and how can we come up with certain interesting formulations? And then how exactly does the nonlinearity of a receiver affect its capacity limits? So that was the first part of my talk. Turns out nonlinearity can severely impact performance. So next, having known that it actually impacts performance and having developed the representations which allow us to track actually how the nonlinearity affects me, can I do my allocations so that I can maximize my network throughput or minimize the wastage of spectrum. So I presented a particular framework which takes into account the adjacent channel interference faced by all receivers depending on their characteristics, which was the nonlinearity and the preselector filter, and then did allocations based on that. And I showed that it actually improves the performance a lot. So this is what I conclude my talk with. I hope this inspired you more to look at receivers also, in addition to all the other network parameters in designing wireless networks. So thank you. I would be glad to address any questions.
There's actually two ways that signals get splattered around in receivers. One way is certainly nonlinear. The other one, which is often worse, is reciprocal mixing. Have you confronted reciprocal mixing?
I have not done in this talk, but by reciprocal mixing, you mean the interactions between the transmitter and the receiver itself, right?
No. What I mean by reciprocal mixing is the phenomenon that the phase noise in local oscillators spreads around the spectral power of strong interferers.
Yes.
Right? So this even a perfectly linear receiver could experience this difficulty due to its own poor phase noise in the LO. And in many receivers, this actually is the dominant problem with respect to this issue you're raising of obfuscation of spectrum. Right? So, to what extent do you address this?
Yes, my predecessor, Yosius, many of you here may know. So he had developed a model for image frequency, to track image frequency and phase noise. And I have used that model. I have not addressed that in this particular talk, but I have used that model and then also done a similar kind of analysis for frequency allocation. So I don't do any analysis on how exactly the reciprocal mixing or the image frequency affects the desired channel. That was done by my predecessor. I just used his model and then did dynamic spectrum allocation frameworks, in which I can utilize that and then do spectrum.
So I just wondered broadly, do you characterize this as a lesser problem, an equally important problem, or a bigger problem than the splatter due to nonlinear?
So long as the signals don't enter, my received power doesn't enter the nonlinear regions, the reciprocal mixing and the image frequency matter more. But as I enter my nonlinear regions, even the weak nonlinearity, the third order intermods dominate over the reciprocal mixing. That is my experience.
I imagine it depends quite a bit on the receiver.
Yes, it depends on the receiver.
Well, a lot of the receivers in which I think this work is probably most applicable probably have pretty bad phase noise. So if you're thinking about handheld receivers doing high data rate stuff, those tend to use LOs that have relatively high phase noise far out.
Yes.
Just one more point is this is just a caution, not really a question, but it's in the RF community, intercept point is not considered a reasonable way to predict spectral splatter. The appropriate use of intercept point, I would say, among RF engineers is as a metric for comparing two receivers. So you compute their second order intercept, compute the third order intercept, you say one receiver has a higher IP2 than the other, it's better in that respect. I don't think you would find an experienced RF engineer who would say you can take IP2, IP3 and use that to estimate splattering, the characteristics of splattering. In fact, there's a prominent paper on this topic, which I'll point out. It's, the name of the paper is The Intercept Point Deception. It's a pretty blunt title. But it talks about this misuse. I think you're probably just short of that line of misusing it, but I think you're very, very close to that line, so I want to point it out.
No, I don't use the intercept point to estimate the spectral splatter. I come up with a combinatorial analysis, but the power levels of the intercept point or power levels of the spectral splatter is determined by the alpha 3 component. So what I do is, say I have n signals, and if I cube it, how does it look in the frequency domain? So if and then I take the FFT of it, how does it look in the frequency domain? So can I do a combinatorial analysis of it? So that's how I approach in actually estimating the spectral splatter. It is not from the IIP3 itself, but IIP3 I just use to scale down the amplitudes of the third order intermodes. I don't use IIP3 to estimate the spectral splatter itself. But yeah, I understand it's very good.
So I consider two kinds of receivers where the reception band is different on both of them. One has very minimal and the other is accepting broad range of things. So how does the interference affect these both? Like in these two cases, how is it different?
So it depends on what signals both of the receivers receive.
Yeah.
But if you
because my intended signal is in one particular band and one of my receiver is receiving that, the other has wider band, but the intended signal is just the small.
Yes.
The same thing.
Yes. So
the interference in both the cases.
Yes. So if I go back here. Yeah, here. So what you're talking about is compared to my pre-selector filter, which is B and W. So this analysis takes care of that because I come up with the adjacent channel interference as a function of W by B, so which is beta. So it automatically takes care.
Which one would be better? Which receiver would perform better?
For the same characteristics, of course, a smaller pre-selector filter will perform better. So for the same received power.
Yeah, so then we can restrict our receivers to that particular thing solve.
So yeah, that goes into receiver regulation. That's a whole different topic.
When you can't regulate all receivers to be within
Yeah.
a particular band, right? Your receiver sensitivity might be different. For example, a GPS receiver won't be a single system. But if they are coexisting, then it's...
No, but if my Wi-Fi receiver is there,
Yes.
or any particular, so I will consider the interference from other Wi-Fi things.
No, what
That is different.
Multi-band.
That is different. That problem is looked into from a lot of years. So there are lots of issues there, yes, as you rightly pointed out, but most of it is co-channel. So in my own small narrow band, what is the interference that I face?
Yeah, because even in the analysis that you perform, the LT is performing better.
Yes.
Might be the reason because it's the frequency that is using is very limited. The band that has been widely used.
Yes, it is not my LT receivers are very selective.
Yeah.
That is the reason. But Wi-Fi receivers are not.
And why did you consider third order nonlinearity? Is there a specific reason for that? Because we have many second and fourth.
Yes. So second order nonlinearity is a square term. It does not produce any distortions in the in-band region. So second order nonlinearity, so if I have an omega as my frequency, second order nonlinearity produces terms in 2 omega or 4 omega, something like that. So it is out of band. But odd order nonlinearities, third, fifth, seventh, they cause interference in band because of the frequency separation, as I showed before. It makes sense to consider not just third order but also fifth, seventh, and others. But the amplitudes of fifth, seventh are relatively much lesser than the third order itself. So third order causes the maximum damage.
Really nice and enlightening talk.
Thank you.
You think, can you please go back to, to the slide number 38? Yeah, here the first line, you have that difference of convex functions, right?
Yes.
So where do you do bounding this? You can directly solve the DC.
Well, rho n is not very, that rho n term there, that is not a well-behaved function.
Oh, that is exactly function.
That is a nonlinear. That is a nonlinear function. So it's not very well-behaved.
Okay, so the optimizing variable is a function of
Rho n.
Yes. Okay, and the next slide. So this particular algorithm is probably simplex algorithm.
Well, I call it a greedy algorithm. Simplex is usually, I think, reserved for linear.
Oh, no, it's Hungarian.
Maybe. I don't think it is.
Okay, so the thing is, you can always relax your variable, optimization variable, not to have binary values. And then after solving the problem, in a continuous domain, you can map into the 0 or 1. So what is the difficulty with that?
There's no difficulty. I just didn't choose to do that. And yeah, and secondly, the complexity also matters a lot. Whether it makes sense and how much sense does it make. And
what you are telling is essentially LP rounding, right?
So LP relaxation, and then yeah, it is
rounding the solution.
My objective with this, when I published this paper, my objective with this was not to come up with the best algorithm. My objective was to highlight more on considering receiver nonlinearity in the framework. So, of course, this is not the, I told this is not the optimal algorithm. This is just an algorithm which gives some performance.
Since these are the signals which fall in the preselector filter of a receiver, so can you come up with a better decoding for your own signal by decoding all other signals in your preselector filter?
So that means I need to know what all other preselector filters are, what all the other signals are. So that means I probably need to have more than one RF chain to decode every signal. It is a possible thing. I had proposed that in my prelims as a future work. So thank you for pointing that out. But it may be possible, may not be possible, I don't know. Because there are different kinds of signals. We have to look into it. They are not same technology. So decoding such interference is not very easy.